Okay, section 2.2, the algebra of functions. All right, so let's mess with your head a little bit here. Up until this point, you've learned a lot in math, right? One of the things that you learned was how to add, subtract, multiply, and divide numbers, right? Okay, well, I'm trying to convince you that functions are actually the new numbers, okay? As far as we're concerned, in algebra and beyond, a function operates very similarly to numbers. So don't be surprised when you see some weird notation. For instance, if you see something that looks like this, f plus g of x, that's not multiplication, right? Just like f of x is not multiplication. That just means this is what you're plugging in. Anyway, okay, so f plus g of x just means that you're going to take your two functions and add them together. That sometimes involves combining like terms and stuff like that. But that's what that means, f plus g of x. You add two functions together to make a new function. Same thing is true with f minus g of x. Honestly, this doesn't even need to be its own set of notation, but I do want you to know what that means. Okay, just that means to subtract them. Okay, f g of x means f of x times g of x, right? In this case, you multiply them together. And then finally, f over g of x just means f of x divided by, or over, like a fraction, g of x. We do have to make a little disclaimer here, right? Provided g of x does not equal 0, right? Because you can't divide by 0. So you want to make sure that doesn't happen. All right, so those are some new notation, right? Those are some new notation. Okay, so let's actually go and do an example, or several examples, right? So example number one, we're going to say f of x is x squared minus 1. And let's say that g of x is 2x plus 5. Let's go through and actually find f plus g of x and all the other ones. Okay, so let's start off with that. F plus g of x. Remember what that means. F of x plus g of x, right? Well, we know what f of x is, and we know what g of x is. F of x is x squared minus 1, plus g of x is 2x plus 5. Okay, so sure, I write them out like that. Let's combine like terms. I see this -1 and this +5. -1 plus 5 is 4. So f plus g of x is equal to x squared plus 2x plus 4. Not too bad. While we're at it, let's also evaluate when x equals 1. Sure, why not? So if, let's say I wanted to find, what I'm asking here, let's say I wanted to find f plus g of 1, right? Again, this is a new function, so I'm allowed to plug stuff into it. Okay, plug it in like we would the old way, right? X squared becomes 1 squared plus 2 times 1 plus 4. So that's 1 squared is 1, 2 times 1 is 2, plus 4, 1 plus 2 is 3, plus 4 is 7. So f plus g of 1 is 7. Cool, let's go on to part B. Let's find f minus g of x. Okay, f minus g of x, again, it's just f of x minus g of x. And I know what f of x is. It's x squared minus 1. And g of x is 2x plus 5. Now I want to be careful here, right? This minus sign applies to the entire g of x, right? So I'll put that in parentheses to remind myself that that minus sign applies to the whole thing, not just the first term, right? If it were just a 2x, it would look like minus 2x plus 5. But no. It's 2x plus 5. All of that is being subtracted. In other words, I have to distribute the negative, right? So that becomes x squared minus 1 minus 2x minus 5, right? That's the big difference there. All right, and then negative 1 minus 5 are like terms. Negative 1 minus 5 is a negative 6. So f minus g of x is equal to x squared minus 2x minus 6. All right, while we're at it, again, let's evaluate. Let's find f minus g of 1, now that we have the formula. 1 minus 2 minus 6. 1 minus 2 is negative 1, minus 6 is negative 7. Okay, so positive 7 and negative 7. All right, let's keep going. Part C. I'm gonna need another page in a second here. Part C, let's find f times g of x. Remember, that means f of x times g of x. And so that's going to look like x squared minus 1 times 2x plus 5. Let's go ahead and distribute to figure this thing out. Expand it out, I should say. X squared times 2x is 2x cubed. X squared times 5 is 5x squared. Negative 1 times 2x is a negative 2x. Negative 1 times 5 is negative 5. Okay, and I actually don't have any like terms there, so I can't simplify it any further than that. That is f times g of x. And of course, as promised, let's find f times g of 1. Let me bring this down so they're on the same line. Okay. I'm just trying to make this look nicer than I need to. Oh well, whatever. All right, so fg of 1, so I'll plug in 2 times 1 cubed plus 5 times 1 squared minus 2 times 1 minus 5. All right, 1 cubed is 1 times 2 is just 2. 1 squared times 1, or 1 squared is 1 times 5 is 5. 2 times 1 is 2. Oh, look at that. 2 minus 2, 5 minus 5, it's 0. Nice. All right, let's go on to another one. Part D. Let's say f of x. Ah, okay. What's happening here? All right, this is a little different notation, but we know that's f of x times f of x. In other words, x squared minus 1 times x squared minus 1. X squared times x squared is x to the 4th. X squared times negative 1 is negative x squared. Negative 1 times x squared is negative x squared. Negative 1 times negative 1 is a positive 1. I do have like terms here, right? Negative x squared minus x squared. That's negative 2x squared plus 1. All right, so f of x is x to the 4th minus x squared plus 1. All right, while we're at it, what is f times f of 1? 1 to the 4th minus 2 times 1 squared plus 1. 1 to the 4th is 1. 1 squared is 1 times 2 is 2 plus 1. That's going to be 0 again, right? 1 minus 2 is negative 1 plus 1 is 0. Nifty. All right. Super long example here, right? Part E. Let's find f over g of x. This is everybody's favorite and least favorite at the same time. F of x is x squared minus 1. G of x is 2x plus 5. Can't do anything else. That's it, right? So there's that. What about f over g of 1? All right, 1 squared minus 1 over 2 times, oops, wrong button, 2 times 1 plus 5. 1 squared is 1, minus 1 is 0. 2 times 1 is 2, plus 5 is 7. 0 over 7 is 0. We're getting a lot of zeros here. All right, I promise, the last one of these, and then we'll move on to another type of example, which is actually the last type. Let's find g over f of x. Reversed it. I flipped it over. So g is on top. F is on the bottom. Again, that's really all I can do there. Well, what is g of f of 1? 2 times 1 plus 5 on top. 1 squared minus 1 on the bottom. We already know the top is 7. Bottom is 0. Oh, that's not defined, right? You can't divide by 0. So you'd say that answer, that solution, is undefined. Okay, so we pretty much went through one of each type of example. In some cases, we did two of the same type, right? Like f of x and g over f of x. Those are kind of the same type of questions. All right, so I did say these are new functions that have their own set of properties, right? You can plug in numbers and find answers to them. Okay, they also have their own domains, okay? So we remember in chapter 1, we talked about the domain of functions. Well, let's talk about now the domain of these new functions, right? These new combined functions. And we're going to use the same ones as before. So let me write them down real quick. F plus g, well, let me start off with f of x. So f of x is x squared minus 1. G of x is 2x plus 5. F plus g of x is x squared plus 2x plus 4. F minus g of x is x squared minus 2x minus 6. We had f times g of x, and that one came out to 2x squared plus 5x, nope, x cubed, not squared, x cubed plus 5x squared minus 2x minus 5. We had f times f of x. F times f of x came out to be x to the 4th minus 2x squared plus 1. We had f over g of x. That was x squared minus 1 over 2x plus 5. We had g over f of x, which was 2x plus 5 over x squared minus 1. I think that covers all of them. Okay, let's find the domain of each of them. And you'll see that it's actually really simple. All right, so if you're trying to find the domain of a new function that's combined, the other two combined, it's where the two functions overlap, right? Where the two original functions overlap. Where the domain of f and the domain of g overlap, or their intersections. Okay, so what does that look like? First of all, let's look at f of x. The domain of f of x is all the numbers, negative infinity to positive infinity, right? Remember how you find domain. You think about all the possible numbers on the number line, and then you look to see, am I dividing by 0 anywhere? Or is there a possibility of getting a negative under a square root? If neither of those two things are present, you have no restrictions. Your domain is negative infinity to positive infinity. Okay, so that's my domain for f. My domain for g is going to be the same thing for the same reason. All right, now we get to the new ones. Okay, so I'm going to draw these out in number line form, right? Domain of f is negative infinity to positive infinity. Let's color code that. Why not? Domain of f is negative infinity to positive infinity. The domain of g, negative infinity to positive infinity. All right, so then what is the domain of f plus g of x? Right, like that. Well, it's going to be where the domain of f, don't need that, and the domain of g overlap each other. They overlap each other everywhere, right? So my domain is negative infinity to positive infinity. All right, that's pretty much the case for all of them because it's the same thing, right? All of them, where did they overlap? Oh, where do these overlap? Where does f times f overlap? Okay, well, in this case, I'll be a little different. All right, f is this red one here that goes forever left and right. And then if I overlap, or I put the other f right on top of it, oh, they're the same thing. Of course they're going to overlap everywhere. All right, the only time things get little weird is when you're dealing with the fraction ones. Because remember, you can't divide by 0. So let me write those out. F over g of x equals x squared minus 1 over 2x plus 5. Okay, the red one, f of x, has all the real numbers. The blue one, g of x, has all the real numbers, which means that they would overlap everywhere. But what happens when we overlap them? Now we're in a situation where we may end up with 0 in the denominator. Okay, so we need to account for that. We have a restriction all of a sudden. The restriction would be any x value that causes the denominator to equal 0. Okay, well, what is that restriction? Negative 5 over 2. Negative 5 over 2 is my restriction here. So there's a hole in the domain there. It breaks my domain into 2 segments as it used to. The first segment spans from negative infinity up until negative 5 over 2. The second segment spans from negative 5 over 2 to infinity, union in between. So that's the domain of f over g. What about g over f? Last one here, g over f. Okay, so just like before, the domain is going to be all the real numbers except any restriction that results from putting x squared minus 1 in the denominator. So I need to solve x squared minus 1 equal to 0 to figure out what my restrictions would be. Okay, add 1 to both sides. Square root both sides. The square root property says that if I take the square root of both sides, I end up with a positive and a negative square root of that number. Well, the square root of 1 is 1. Why is that? Because negative 1 squared is positive 1. Positive 1 squared is positive 1, right? So there's 2 instances that would give me a positive 1. All right, so we have 2 holes in the domain, negative 1 and positive 1. That breaks my domain into 3 segments. 1, 2, and 3. So the domain of g over f is negative infinity to negative 1. That's the first segment. Union, negative 1 to 1. That's the second segment. Union, 1 to infinity. That would be the third segment. Okay, so the domain question, it's a little tricky. Just remember, look at the domain of the original 2 functions. Check to see what would happen if I combined them. right? If I put one on top of the other, most of the time they're going to be negative infinity to positive infinity. If one of them has a hole in their domain, well, then just include that in the combined domain, okay? If two of them have a hole in the domain, let me write that out. Let's say, for example, right? So totally different example, and not a full example. Let's just say you had your first domain that was negative infinity, positive infinity, but had a hole in the domain at 2. Okay, so there you go. Got a hole in the domain at 2. And then you had another one that had negative infinity, positive infinity, had a hole in the domain at -5. Okay, so there we go, -5 and 2. So the new one, right, the new domain, the domain of your new function, would have a hole in the domain at -5 and at 2. Okay, so you're just going to combine them. Okay, so I wanted to make sure I talked about that. The only time that's going to be anything where it requires a little extra work is whenever you have the fraction ones, right? So you look at the denominator of the new fraction that you just made, set it equal to 0. That'll tell you if there's any other holes in the domain. All right, and that's section 2.2.